you've just built an incredible AI feature. It works, flawlessly in your local Jupyter notebook.
Oh, yeah. Best feeling in the world.
Right. You throw a prompt at it, and boom, it writes a complex SQL query, or summarizes a dense PDF, or generates this perfect block of code. It feels like absolute magic.
It really does, until you share it.
Exactly. The second you push that code to a production server and say 100 real users try to access it concurrently, your entire system just catches fire. It crashes and burns to the ground.
Complete meltdown, usually with a lovely 500 error.
Yeah. So welcome to the late night architecture session. If you are listening to this right now, chances are you're a software engineer, you've got a glowing monitor casting a shadow across your desk, and you are staring down the barrel of an AI deployment.
Which is incredibly daunting the first time you do it.
It is. So today we are taking a deep dive into crossing that massive chasm between a local prototype and a hardened, scalable AI system. And we're drawing on the architecture blueprints from the 120 LLM Mastery Guide to do it.
Yeah, and that chasm between prototype and production, it's really the defining engineering challenge of the moment.
For sure.
Because it requires a fundamental rewiring of how we think about back-end infrastructure. I mean, the intuition you've developed over years of building standard web applications, microservices, REST APIs.
All the standard stuff.
Right. A lot of that actually works against you when you start serving large language models.
Let's map this out from a traditional software engineering perspective. Because as engineers, we're used to solving traffic spikes with horizontal scaling.
Just throw more servers at it.
Exactly. If my Node or Django app is getting crushed by requests, I don't panic. I just throw an Nginx load balancer in front of it, spin up 10 more AWS instances or, Kubernetes pods, and I just let the CPU handle the context switching.
Which works beautifully for stateless web apps.
Right. We've been scaling CRU'd apps like this for over a decade.
Yeah.
So why can't I just wrap my Python LLM script in a Docker container, duplicate it, and call it a day?
Well, because the bottleneck isn't standard compute logic. It's memory bandwidth.
Memory bandwidth. Okay, explain that.
So to understand why standard scaling fails, we have to look at what the hardware is actually doing under the hood. When you spin up a traditional web server, the CPU is, fetching a few database rows, executing some conditional logic, maybe rendering HTML or JSON, and firing it back.
Super lightweight.
Incredibly fast. It's built for context switching between thousands of lightweight requests, but an LLM running on a GPU is performing massive sequential matrix multiplications for every single word or token that it generates.
So it's computationally heavy, but how does that actually break standard concurrency?
It breaks because it is entirely memory bound.
Ah.
Let's use a physical space analogy here.
Okay, I like analogies.
Imagine your GPU is a commercial kitchen counter. A standard web request is like a tiny sticky note with an order on it.
Right, like one burger, no pickles.
Exactly. You can stick thousands of those notes on the counter, and the chef, which is the CPU, can quickly glance at all of them and just manage the workload effortlessly.
Makes sense.
But an LLM request isn't a sticky note. It's a massive 10-course recipe book that has to be laid out completely open on the counter.
Oh, wow.
Yeah, we call this the context window. And the GPU has to store the entire state of that conversation in its memory, specifically in something called the KV cache, or key value cache.
Okay, that makes the constraint highly visual. The physical memory on the hardware, like the VRAM, that's our counter space.
Yes, and VRAM is finite and, frankly, incredibly expensive.
Yeah, no kidding.
So if 100 concurrent users hit your AI feature, a standard load balancer just dumps 100 of those massive recipe books into the kitchen at the exact same millisecond.
Which would literally cover the entire counter instantly.
Exactly. In a standard web app, the system just queues the sticky notes up. But in an LLM serving environment, your GPU immediately runs out of physical VRAM trying to open all those books at once.
So it just panics.
You get an out-of-memory error, the process dies, and the whole system crashes with a 500 error. You didn't run out of compute power, you just ran out of counter space.
Which means we really can't just treat the AI model like another microservice.
Not at all.
If VRAM is the ultimate bottleneck, then we need a radically different way to manage the traffic before it even touches the GPU, right? We have to become obsessive about how requests are scheduled and processed.
You have to be absolutely ruthless about scheduling, which brings us right into the engine room of AI serving. and specifically to a technique called continuous batching.
Continuous batching. Okay, let's dig into that.
It is arguably the most critical optimization for keeping an LLM in production without going completely bankrupt.
Always a good goal.
Right. To appreciate what it does, though, we first have to look at how naive batching works.
Okay, how does that look?
In standard machine learning inference, you might group, say, 8 requests together into a static batch and send them to the GPU. The GPU processes them in parallel. But LLM generation is sequential. It predicts one token, then uses that new output to predict the very next token.
Right, it's an autoregressive process. It basically feeds on its own output.
Exactly. Because of that sequential nature, static batching forces all 8 requests in the batch to completely finish generating before the GPU can load the next batch of requests.
Wait, so they're all tied together?
Yes. Think about a single-file line at a grocery store. If the person at the front of the line is paying entirely in pennies, everyone else behind them is just stuck waiting.
Oh, that sounds awful. Let me translate that into prompt terms for you listening. If one user in that batch of 8 asked the model to write, I don't know, a sprawling 5,000-word essay on the Roman Empire.
That happens all the time.
Right. And another user in the exact same batch just asked the model to translate a 3-word sentence into French. You're saying the user wanting the quick translation has to wait for the entire 5,000-word essay to finish printing token by token before the batch is released.
That captures the frustration perfectly. But technically, from an infrastructure perspective, it's even worse than just a bad user experience.
How could it be worse?
It's an architectural sin. As the model is finishing up the last few paragraphs of that long essay, the other 7 requests in the batch have already hit their stop tokens.
Right, they're done.
So that means 7/8 of your incredibly expensive GPU compute capacity is sitting completely idle, just waiting for the longest sequence to finish.
The cashier's just staring at the wall while the one guy counts his pennies. That's brutal. So if static batching holds everyone up and wastes VRAM, couldn't we just operate at the token level?
What do you mean?
Like, instead of waiting for a full response to finish, what if the system spits out a token, checks the queue, and swaps users in and out on the fly?
You've just deduced continuous batching.
Oh, nice.
That is exactly how it works. Instead of operating at the request level, the engine operates at the iteration level. It's an asynchronous dynamic scheduling loop.
Okay, so how does it handle the French translation gap?
The millisecond the French translation hits its final token, the continuous batching engine evicts its KV cache. It clears that recipe book off the counter and immediately injects a new user's prompt into the active batch for the very next token iteration.
Oh, wow. So it's dynamically shuffling the line at the register in real time. It doesn't wait for the essay to finish.
Exactly.
It just kicks the completed request out, frees up the VRAM, and pulls the next person's request in without skipping a beat on the essay generation.
And by doing that, you keep the compute engine completely saturated. Your GPU is always working on a full, dense matrix of tokens simultaneously.
That makes so much sense.
Yeah, you are maximizing your hardware utilization, which is really the only way to make the economics of running an LLM work at scale.
Okay, so here's where it gets really interesting for the front-end developers listening, because we've heavily optimized the back-end now. We are utilizing the GPU effectively, managing the VRAM, and keeping the servers from crashing.
The back end is purring.
Right. But a hyper-optimized backend doesn't matter at all if the user sitting at their screen thinks the app is frozen and just closes the browser tab.
Oh, totally.
We have to talk about the front-end UX imperative here, which is streaming tokens.
Yes. This is where back-end reality and human psychology collide.
Collide hard.
Yeah. Generating tokens sequentially takes time, even on the absolute fastest H100 GPUs. If a user asks a complex question, the model might take 10 or 15 seconds to fully compute the response.
But okay, as a front-end dev, I might argue, why is that actually a problem? We've trained users to look at loading spinners for 2 decades.
Sure.
Why not just, await fetch, wait for the full JSON payload to return like every other REST API,
Yeah.
and render it all at once? I mean, does progressive text actually solve a hard technical problem? Or is it just a psychological magic trick to keep the user entertained?
Well, it is heavily psychological, but that psychology solves a critical technical vulnerability.
Okay, how so?
If you force a user to stare at a static loading spinner for 15 seconds in an AI context, they won't patiently wait. They will assume the system has hung.
Which is fair. It feels like a long time.
Right. And what does a user do when a web page hangs?
They hit refresh.
And when they hit refresh, they abandon the current connection and send a brand new, highly complex prompt to your backend.
Oh, no.
Yes. Now your GPU is processing the original abandon request and the new duplicate request.
Wait, really? It processes both.
Yep. If 100 users do that, you've just doubled your active context windows and triggered the exact VRAM crash we were trying to avoid.
Wow, so streaming isn't just a UI flourish. It's a systemic load-bearing mechanic.
It is absolute infrastructure protection. By streaming the tokens via server-sent events or WebSockets, you give the user immediate visual feedback.
Right, they see things happening.
Exactly. We measure this with a metric called time to first token, or TTFT.
TTFT. Got it.
In the AI era, TTFT is the new time to interactive. If you can stream that very first word to the user's screen in under 1 second, they start reading. Their brain is engaged.
So a 15-second total generation time feels completely instantaneous because they are reading the text as it literally appears.
Precisely. You manage human patience, which directly protects your VRAM from duplicate refresh requests.
That is brilliant. Okay, so we have a unified, optimized flow now. We've pulled the prototype out of the Jupyter notebook. We are managing the physical VRAM constraint with continuous batching, which prevents bottlenecks.
Check.
And we are protecting the system from impatient users by optimizing for a sub-second time to first token through streaming. It's fast, it's responsive. But let's look at reality for a second.
Reality is always messy.
Yeah. What happens when we get featured on a massive tech blog and traffic spikes 100x overnight? Because no matter how good our continuous batching is, VRAM is still finite.
It is, and this brings us to the principle of graceful degradation.
Graceful degradation. I like the sound of that.
When a massive traffic spike hits, your system must bend, not break. In a standard web application, graceful degradation might mean, turning off a heavy analytical dashboard or serving slightly lower resolution images.
Right, dropping non-essentials.
But in an AI architecture, bending means making difficult trade-offs between quality, latency, and uptime.
I want to dig into that because the standard tactics make sense to me. Like rate limiting is obvious. Cap how many requests an IP can make.
Yeah.
Queue management makes sense too. If the continuous batching engine is completely full, we place incoming requests into a priority queue, maybe prioritizing paid tier users.
Standard operational practices, yeah.
But there's a third tactic mentioned in the guide that feels highly controversial for a software engineer.
You're talking about model downgrades.
Yes.
Yeah.
Model downgrades. That sounds wild.
It is controversial, but it's a vital survival mechanism. The concept is basically dynamic routing. If your system health checks detect that GPU VRAM utilization is sitting at, say, 95% and the queue is backing up, you automatically reroute incoming requests away from your massive state-of-the-art primary model and send them to a smaller, less capable model.
See, as an engineer, that hurts my pride.
I know.
If a user asks a complex coding question, I want them to get the absolute best answer from the massive 70 billion parameter model. If you secretly route my prompt to a tiny 8 billion parameter model just to save server load, I'm going to get a worse, less nuanced answer. Isn't that a terrible user experience?
It is a compromise in nuance, without a doubt. But compare it to the alternative.
Which is crashing.
Exactly. If you don't route to the smaller model, VRAM exhausts, the server throws a 500 internal server error, and the user gets absolutely nothing.
Yeah, a blank screen is worse than a slightly less eloquent answer.
In a production emergency, receiving an immediate answer is infinitely better than an outright crash. It's about prioritizing reliability. A 99.9% uptime with a smaller model during a spike is a vastly superior engineering achievement than a 0% uptime with a brilliant model.
Okay, fair point. So how are we actually executing these smaller models? Are we just keeping completely different architectures on standby on separate servers?
Sometimes, yes. But more often, we rely on a technique called quantization.
Quantization.
This is a crucial concept for engineers to understand. Neural network weights are typically stored as high-precision 32-bit floating point numbers.
Right, standard floats.
And that requires a massive amount of memory. Quantization is essentially rounding down the math. We compress those weights from 32-bit floats down to 16-bit or even 8-bit integers.
Wait, so we are intentionally reducing the mathematical precision of the neural network just to shrink its physical footprint.
Precisely. An 8-bit quantized model takes up a fraction of the VRAM and executes dramatically faster because integer math is way cheaper than floating point math.
Oh, that makes sense.
You lose a slight amount of accuracy, sure, but you gain massive throughput. During a traffic spike, swapping to an aggressively quantized model is what keeps your infrastructure alive.
But wait, if we want to speed things up without losing that precision, isn't there another way? I've seen discussions around speculative decoding. How does that fit into this architecture?
Oh, speculative decoding is brilliant. It's a way to balance the speed of a small model with the quality of a massive model.
How does it do both?
Instead of just downgrading, you use a tiny, lightning-fast draft model to quickly guess the next 5 or 10 tokens.
Okay.
Then you pass those guess tokens to your massive, highly accurate model. The large model evaluates all those guess tokens in parallel in a single forward pass.
Wait, so it checks the draft model's homework?
Exactly. If the small model guessed correctly, the large model accepts them, and you just generated 10 tokens in the time it usually takes to generate one.
That's incredible. It's like having a junior developer quickly write a draft function, and a senior architect just glances at it and says, yep, looks good, ship it.
That is the perfect analogy. And if the junior dev makes a mistake, the senior architect just corrects it on the spot.
Man, that is so clever.
It requires complex orchestration, obviously, but it allows you to dramatically increase throughput without sacrificing the high-quality output of your best model.
Which brings us to the operational reality of managing all this complexity.
Yeah.
Because we're talking about swapping models, quantizing weights, speculative routing. This isn't just, updating a Docker container.
No, not at all. It requires a specialized operational discipline known as MLOps.
MLOps,
Yeah.
machine learning ops.
Yeah, and MLOps is not just DevOps with a new coat of paint. In DevOps, your primary artifact is your deterministic code. In MLOps, you must treat the AI model, the massive gigabyte-scale weights, as a first-class artifact right alongside your application code and infrastructure.
Let me put that in SWE terms for you listening. Imagine trying to run Git for a 40 gigabyte neural network. You can't just commit a diff of the weights like you do with a JavaScript file.
You hit the nail on the head. You need dedicated infrastructure for model versioning. If you deploy a newly fine-tuned version of your LLM and it starts misbehaving or hallucinating in production,
Which they love to do.
you need the ability to hit a rollback switch instantly, routing traffic back to the previous stable weights.
But how do we even know if it's misbehaving? With standard code, if I deploy a bug, my unit tests fail, or my error logs light up with stack traces. But if an LLM is silently generating bad advice or poor code, it doesn't throw a stack trace.
Exactly. It doesn't know what's wrong.
Right, it just returns a perfectly formatted 200 OK response with terrible text inside.
That is where A/B testing and drift monitoring come in. You
Yeah.
can't rely on standard error logs. You have to route, say, 10% of your traffic to a new model version and capture telemetry on how users react.
Like, are they copying the code snippet it generated?
Yes. Are they regenerating the response? That implicit feedback tells you if the model is actually performing well.
And what about drift monitoring?
Drift monitoring tackles the reality that the world changes, but a trained model is frozen in time. Language trends shift, APIs get updated, user behaviors evolve.
Oh, sure. Like a coding assistant trained in 2023 might confidently generate outdated React syntax in 2025.
Exactly. The model's outputs slowly drift away from what is accurate or useful. So MLOps is the rigorous discipline of constantly monitoring that output quality in production and knowing exactly when to retrain or update the weights.
It's a living, breathing component.
Yeah.
It is entirely different from deploying a static algorithm.
Totally different beast.
So what does this all mean when we step back and look at the big picture? Let's connect all these pieces into one unified architecture.
When you look at the whole system, every single technique we've discussed serves one ultimate goal: managing the VRAM bottleneck while keeping the user completely blind to the underlying chaos.
It's a masterclass in constraints, honestly. We start by acknowledging that GPU memory, not compute speed, is our true limit. Because LLMs need that massive KV cache open like a recipe book on a counter, traditional load balancing fails. So, we implement continuous batching in the engine room, swapping requests in and out at the token level, maximizing hardware efficiency so the GPU is never sitting idle.
Then we mask the inherent latency of sequential generation by streaming tokens to the front end.
Oh yeah, getting that time to first token under 1 second.
We obsess over that, using human psychology to prevent users from refreshing and sending duplicate spikes to our VRAM.
And finally, we design for failure. When traffic inevitably surges, we rely on graceful degradation. We rate limit, we queue, and if necessary, we dynamically route traffic to faster, quantized models to ensure the system bends instead of breaking.
And we wrap that entire living ecosystem in strict MLOps practices, versioning our gigabyte scale weights and monitoring for drift.
It is a phenomenal, rigorous roadmap for pulling an AI project out of the local sandbox and deploying it as a true battle-tested production system.
It really is. It takes a lot of work, but it's worth it.
Absolutely. So we've mapped out the architecture, but before we sign off and let you get back to your IDE, I want to leave you with one final puzzle to mull over.
Oh, I love these.
We just talked extensively about the MLO's philosophy of treating the AI model as a first-class artifact alongside your code.
Yeah.
But here is the catch for software engineers to ponder.
Okay.
Standard code dash, your Python scripts, your React components is completely deterministic. An if statement behaves the exact same way every single time you run it.
But an LLM is inherently probabilistic. It is predicting the next token based on statistical weights.
Exactly. It's not deterministic. So
Yeah.
when you go back to your desk to build this out, ask yourself, how do you write reliable automated unit tests in your CI/CD pipeline for a core artifact that is literally designed to hallucinate?
Oh, man. That is the paradox that keeps AI infrastructure engineers up at night.
It really is a murky landscape. But navigating that uncertainty is where the real engineering happens. Good luck on your own deployments, obsess over that time to first token, and make sure you have enough VRAM counter space before you open the restaurant doors. Thanks for joining us on this deep dive.